Hello, lovely students. Today we would walk through a very interesting chapter of grade 9 physics, and that is motion. Welcome to the channel. Walk through the chapter with us, and you would be amazed by the way you get a hang of it without having to make much of an effort. A chapter you'll really enjoy. So, shall we begin? In everyday life, we see some objects at rest and others in motion. Firstly, let's see some objects in motion. Birds fly, fish swim, blood flows through veins and arteries, and cars move. Atoms, molecules, planets, stars, and galaxies are all in motion. An object is perceived to be in motion when its position changes with time. However, there are situations where the motion is not directly visible, or there is no change in place, but is inferred through indirect evidences. For example, we infer the motion of air by observing the movement of dust and the movement of leaves and branches of trees. Now, we know that the phenomena of sunrise, sunset, and changing of seasons is caused due to the motion of the earth. Well, in that case, why don't we directly perceive the motion of the earth? An object may appear to be moving for one person and stationary for some other. For the passengers in a moving bus, the roadside trees appear to be moving backwards. A person standing on the roadside perceives the bus along with the passengers as moving. However, a passenger inside the bus sees his fellow passengers to be at rest. What do these observations indicate? Most motions are complex. Some objects may move in a straight line, others may take a circular path. Some may rotate, while a few others may vibrate. There may be situations involving a combination of these kind of motions. Let me ask you an interesting question. Are the walls of your house at rest or in motion? Well, the walls are at rest if you stand right in front of it as it doesn't move. But with the rotational movement of the earth, it is in motion. So it can be said that a wall is both at rest and at motion. Let me share a funny experience. I was traveling in a train when it stopped at a station. Suddenly, I felt that the train is moving, whereas it was still at rest. Now, how is this possible? Well, the perception of the motion is relative. It means when an object is moving or the surrounding objects are in motion, then the motion is definitely felt. Hence, sometimes when we are sitting in a vehicle which is not moving, for example, train, and a train passes by parallelly, we would feel that our train in which we are sitting is moving. Similarly, when we are sitting in a train that is moving, we are also moving with it, right? So the relative motion is zero, and hence we feel that the train is not moving, whereas to the person standing outside the train, it would definitely appear to be moving since that person is at rest, and hence the train is in relative motion to him. Do you think motion can be dangerous too? Well, if it is erratic and uncontrolled, it can definitely be dangerous. Like as observed in a flooded river, a hurricane, or a tsunami. On the other hand, controlled motion can be a service to the human beings, such as in the generation of hydroelectric power. We describe the location of an object by specifying a reference point. Let us understand this with the help of an example. We say that India is some X kilometers north of Sri Lanka. We have specified the position of India with respect to Sri Lanka. In this case, Sri Lanka would be the reference point. We could have also chosen other reference points according to our convenience. Therefore, to describe the position of an object, we need to specify a reference point which is called the origin. The simplest type of motion is in the motion along the straight line. The total path length covered by an object is the distance covered by that object. Suppose a bus travels for 35 kilometers from a point O to the point B, and then it turns back and travels 10 kilometers from point B to the point C towards the point O. The total path length covered by the object is OB plus BC, that is 35 kilometers plus 10 kilometers, which is 45 kilometers. This is the distance covered by the object. To describe distance, we need to specify only the numerical value and not the direction of motion. There are certain quantities which are described by specifying only their numerical values. The numerical value of a physical quantity is called its magnitude. The shortest distance measured from the initial to the final position of an object is known as displacement. In our case, displacement would be 35 km minus 10 km, which is 25 kilometers. That is the distance of the final point from the original point. Do you think that the magnitude of the displacement for a course of motion may be 0, but the corresponding distance covered is not 0? Let us know in the comment section below. Thus, two different physical quantities, the distance and the displacement, are used to describe the overall motion of an object and to locate its final position with reference to its initial position at a given time. Automobiles are fitted with a device that shows the distance traveled based on the perimeter of the wheel as the wheel rotates. Such a device is called an odometer. Most odometers work by counting wheel rotations and assume that the distance traveled is the number of wheel rotations times the circumference, which is the standard tire diameter times pi. If a car is driven from Gurugram to New Delhi and the difference between the final reading and the initial reading of the odometer is 50 kilometers, what would be the magnitude of the displacement between Gurugram and New Delhi? To find the magnitude of the displacement, measure the straight line distance between Gurugram and Delhi on the map of India. Then convert the straight distance into kilometer as per given scale in the map. Let's discuss this scenario. A farmer moves along the boundary of a square field of side 10 meters in 40 seconds. What will be the magnitude of displacement of the farmer at the end of 2 minutes 20 seconds from his initial position? Perimeter of the field is 40 meters. 2 minutes and 20 seconds would be 140 seconds. Distance covered in 40 seconds is 40 meters. So the distance covered in 140 seconds would be 140 meters. If the farmer starts moving from point A after 140 seconds, he would have completed 3 full rounds in 120 seconds, returning back to point A, and then covering half the field in 20 seconds, reaching point C. Displacement would be a straight line from A to C. Therefore, displacement AC would be 14.14 meters. The calculations are shown on the screen. Thus, after 2 minutes 20 seconds, the displacement of the farmer will be equal to 14.14 meter northwest from initial position. Do you think that it is true that displacement cannot be zero? Or do you think it is true that the magnitude of displacement is greater than the distance traveled by the object? Let us know in the comment section below. Okay, tell me this. In an hour, what is the displacement of the minute's hand of a clock from its original position? Think and write in the comment section. Remember this, the magnitude of displacement is always less than or equal to the distance traveled. If you're liking the video, please hit the like button and don't forget to subscribe and share. As the object covers an equal distance in equal interval of time, it is said to be in uniform motion. The time interval in this motion should be small. Consider a turtle moving along a straight line. Let it travel 5 centimeters in the first second, 5 more in the next second, and 5 more in the third second, and 5 more in the fourth second. In this case, the object covers 5 centimeters in each second. So, what does the path of an object look like when it is in uniform motion? Well, an object with uniform motion has a straight line path. In our day-to-day life, we come across motions where objects cover unequal distances in equal intervals of time. For example, when a car is moving on a crowded street or a person is jogging in a park. These are some instances of non-uniform motion. Measuring the rate of motion. Different objects may take different amounts of time to cover a given distance. Some of them move fast and some move slowly. The rate at which objects move can also be different. Also, different objects can move at the same rate too. One of the ways of measuring the rate of motion of an object is to find out the distance traveled by the object in unit time. This quantity is referred to as speed. The SI unit of speed is meters per second. This is represented by the symbol m by s. The other units of speed include centimeters per second or kilometers per hour. To specify the speed of an object, we require only its magnitude. The speed of an object need not be constant. In most cases, objects will be in non-uniform motion. Therefore, we describe the rate of motion of such objects in terms of their average speed. The average speed of an object is obtained by dividing the total distance traveled by the total time taken. If an object travels a distance t in time t, then its speed is d by t. Let us understand this with the help of an example. Suppose a car travels a distance of 100 kilometers in 2 hours. Then its average speed would be 100 by 2, that is 50 kilometers per hour. The car might not have traveled at 50 kilometers per hour all the time. Sometimes it might have traveled faster and sometimes slower than this. Let's consider one more example. An object travels 16 meters in 4 seconds and then another 16 meters in 2 seconds. What is the average speed of the object? Total distance traveled is 16 plus 16, that is 32 meters. Total time taken is 4 plus 2, that is 6 seconds. Average speed is total distance by total time. Average speed is therefore 32 by 6, and that would be 5.33 meters per second. Therefore, the average speed of the object is 5.33 meters per second. The rate of motion of an object can be more comprehensive if we specify its direction of motion along with its speed. Velocity is the speed of an object moving in a definite direction. The velocity of an object can be uniform or variable. It can be changed by changing the object's speed, direction of motion, or both. When an object is moving along a straight line at a variable speed, we can express the magnitude of its rate of motion in terms of average velocity. It is calculated in the same way as we calculate average speed. In case the velocity of an object is changing at a uniform rate, then average velocity is given by the arithmetic mean of initial velocity and final velocity for a given period of time. Speed and velocity have the same units, that is meters per second. So here is the difference between speed and velocity. You can go through it. If you want, you can pause the screen for a minute to make notes. Moving on, can you guess under what conditions is the magnitude of average velocity of an object equal to its average speed? Well, the magnitude of average velocity and average speed will be the same when the total distance traveled is equal to the displacement. At a time when it is cloudy, there may be frequent thunder and lightning. The sound of thunder takes some time to reach you after you see the lightning. Can you answer why this happens? Well, it's because the speed of light is more than the speed of sound. Hence, light travels faster than the sound. Let's solve this. During an experiment, a signal from a spaceship reached the ground station in 5 minutes. What was the distance of spaceship from the ground station? The signal travels at the speed of light, that is 3 times 10 raised to the power 8 meters per second. Time is 5 into 60 seconds and the speed is 3 into 10 raised to the power 8. And as we know, distance is speed into time. So the distance is 9 times 10 raised to the power 10. Let's see one more example. The odometer of a car reads 2000 km at the start of a trip and 2400 km at the end of the trip. If the trip took 8 hours, calculate the average speed of the car in km per hour and meters per second. Distance covered by the car would be 400 kilometers. Time elapsed is 8 hours. So the average speed is distance by time, that is 400 by 8 and hence 50 kilometers per hour. Converting it into meters per second, we get 13.9 meters per second. Hence the average speed of the car is 50 kilometers per hour or 13.9 meters per second. Let's see one more example. Usha swims in a 90-meter long pool. She covers 180 meters in 1 minute by swimming from one end to the other and back along the same straight path. Find the average speed and average velocity of Usha. Total distance in 1 minute is 180 meters. Displacement of Usha in 1 minute is 0 meters. So average speed is total distance covered by total time taken, which gives us 3 meters per second. Average velocity, however, is total displacement by total time. So it will be like 0 by 60, which is 0 meters per second. So the average velocity of Usha is 0, whereas the average speed is 3 meters per second. Let's talk about rate of change of velocity. In case of non-uniform motion, velocity varies with time. It has different values at different instants and at different points of the path, right? Acceleration is a measure of the change in the velocity of an object per unit time. Suppose the velocity of an object changes from an initial value u to the final value v in time t, then the acceleration is v minus u by t. If the acceleration is in the direction of velocity, it is positive acceleration. Whereas if the acceleration is in the direction opposite to that of velocity, it is negative acceleration. The SI unit of acceleration is meters per second square. If an object travels in a straight line and its velocity increases or decreases, it can be either way. It can increase or it can decrease, but by equal amounts in equal intervals of time. Then it is uniform acceleration. So there are three keywords here: straight line, equal amounts of increase or decrease, and equal interval of time. For example, the motion of a freely falling body. Let's see some examples from our day-to-day lives where we come across a range of motion. Let's first see the example of acceleration in the direction of motion. When an object is freely falling in gravitational field. When an object is projected vertically upward in gravitational field, it will be acceleration acting in the direction opposite to that of motion. Acceleration in gravitational field near Earth's surface is an example of uniform acceleration. If a car traveling along a straight road increases its speed by unequal amounts in equal intervals of time, then the car is said to be moving with non-uniform acceleration. Let's see an example. Starting from a stationary position, Rahul paddles his bicycle to attain a velocity of 6 meters per second in a time period of 30 seconds. Then he applies brakes such that the velocity of the bicycle comes down to 4 meters per second in the next 5 seconds. Calculate the acceleration of the bicycle in both the cases. In the first case, initial velocity is 0 and the final velocity is 6 meters per second. The time taken is 30 seconds. Now we know that A is v minus u by t. Substituting the given values of u, v and t, we get A is 6 minus 0 by 30. That will come out to be 0.2 meters per second square. Now considering the second case after he applies the brakes. The initial velocity was 6 meters per second and the final velocity 4 meters per second. Time taken is 5 seconds. So acceleration would be 4 minus 6 by 5, which would come out to be 0.4 meters per second square. Hence, the acceleration of the bicycle in the first case is 0.2 meters per second square and in the second case it is 0.4 meters per second square negative. Let's consider one more example. A bus decreases its speed from 80 km per hour to 60 km per hour in 5 seconds. Find the acceleration of the bus. The basics remains same. A is v minus u by t. V is the final velocity, u is the initial velocity and t is the time, right? So, initial velocity given here is 80 kilometers per hour. Let's convert it into meters per second. So it will be 22.2 meters per second. Similarly, the final velocity would come out to be 16.6 meters per second. Acceleration would be 16.6 minus 22.2 divided by 5. So it will be minus 1.12 meters per second square. The negative sign indicates that the velocity is decreasing. Therefore, the acceleration of the bus that decreases its speed from 80 km per hour to 60 km per hour in 5 seconds is minus 1.12 meters per second square. How about one more example for better understanding? Let's go. A train starting from a railway station and moving with uniform acceleration attains a speed of 40 km per hour in 10 minutes. Find its acceleration. Time is 600 seconds, initial speed 0, final speed 40 km per hour. On converting, it comes out to 11.1 meters per second. Now acceleration is v minus u by t. Substituting the values, we get acceleration to be 0.0185 meters per second square. Graphs provide a convenient method to present basic information about a variety of events. To describe the motion of an object, we can use line graphs. In this case, line graphs show dependence of one physical quantity such as distance or velocity on another quantity such as time. The change in the position of an object with time can be represented on the distance-time graph, adopting a convenient scale. Let's see some distance-time graphs. In this graph, time is taken along the x-axis and distance is taken along the y-axis. Distance-time graphs can be employed under various conditions where objects move with uniform speed or non-uniform speed, or even if the object is at rest. We know that when an object travels equal distances in equal intervals of time, it moves with uniform speed. This shows that the distance traveled by the object is directly proportional to the time taken. Thus, for uniform speed, a graph of distance traveled against time is a straight line. The portion OB of the graph shows that the distance is increasing at a uniform rate. Note that we can also use the term uniform velocity in place of uniform speed if we take the magnitude of displacement equal to the distance traveled by the object along the y-axis. We can use the distance-time graph to determine the speed of an object. To do so, consider a small part AB of the distance-time graph as shown here. Draw a line parallel to the x-axis from the point A and another line parallel to the y-axis from the point B. Extending the line parallel to the x-axis from point A, these two lines meet each other at point C to form a triangle ABC. Now, on the graph, AC denotes the time interval T2 minus T1, while BC corresponds to the distance S2 minus S1. We can see from the graph that as the object moves from the point A to B, it covers a distance S2 minus S1 in time T2 minus T1. The speed v of the object therefore can be represented as S2 minus S1 divided by T2 minus T1. We can also plot the distance-time graph for accelerated motion. Table here shows the distance traveled by a car in a time interval of 2 seconds. The distance-time graph for the motion of the car is shown here. The nature of this graph shows non-linear variation of the distance traveled by the car with time. Thus, the graph shown represents motion with non-uniform speed. The variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. In this graph, time is represented along the x-axis and the velocity is represented along the y-axis. Velocity time graphs are used to represent the variation in velocity with time for an object moving in a straight line. However, if the object moves at uniform velocity, the height of the velocity time graph will not change with time, as shown here. It will be a straight line parallel to the x-axis. This is the velocity time graph for a car moving with a uniform velocity of 40 km per hour. The product of velocity and time gives displacement of an object moving with uniform velocity. So, the distance s moved by the car in time t2 minus t1 can be expressed as s equal to ac into cd, which is 40 kilometers per hour into t2 minus t1, which is the area of rectangle ABDC. The area enclosed by velocity time graph and the time axis will be equal to the magnitude of displacement. The velocity of 40 km per hour is represented by the height AC or BD, and the time t2 minus t1 is represented by the length AB. For all the uniformly accelerated motion, the velocity time graph is a straight line. The distance traveled by the car will be given by the area ABCDE under the velocity time graph, which would be area of triangle ADE plus area of rectangle ABCD. In the case of non-uniformly accelerated motion, velocity time graphs can have any shape. Figure A shows a velocity time graph that represents motion of an object whose velocity is decreasing with time, while B shows the velocity time graph representing the non-uniform variation of velocity of the object with time. Let's perform an activity. The times of arrival and departure of a train at three stations A, B, and C, and the distance of stations B and C from station A are given. Now, the distance covered from A to B would be 120 kilometers. Time is 3 hours. Average speed is 120 by 3, that is 40 kilometers per hour. Distance covered from B to C would be 60 kilometers. Time would be 1.5 hours and average speed would be 40 kilometers per hour. So speed is same between A to B and B to C. Let's plot the graph now. The graph would look something like this. Let's perform one more activity. Firoz and his sister Sanya go to the school on their bicycles. Both of them start at the same time from their home but take different times to reach the school, although they follow the same route. Table here shows the distance traveled by them in different times. Let's plot the distance time graph for their motions on the same scale and interpret. We can see that the speed of Firoz is better than Sanya. Firoz reaches before Sanya and waits for Sanya. Equations of motion by graphical method. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during the motion, and the distance covered by it in a certain time interval by a set of equations known as the equations of motion. If u is the initial velocity of the object, which moves with uniform acceleration a for the time t, v is the final velocity, and s is the distance traveled by the object in time t, the velocity-time relation can be described by the equation v is equal to u plus at. The second equation represents the position-time relation s equal to ut plus half at square. The third equation represents the relation between the position and velocity and can be obtained from equations 1 and 2 by eliminating t. It is 2as is equal to v square minus u square. These three equations can be derived by graphical method. You can note down these equations as these are very important for the chapter. Consider the velocity time graph of an object that moves under uniform acceleration as shown here. From this graph, we can see that initial velocity of the object is u at point A, and then it increases to v at point E, at point B in time t. The velocity changes at a uniform rate a. The perpendicular lines BC and BE are drawn from point B on the time and the velocity axis respectively, so that the initial velocity is represented by OA and the final velocity is represented by BC and the time interval is represented by OC. Now BD is BC minus CD. This represents the change in velocity in time interval t. From the graph, we observe that BC is equal to BD plus DC, which is equal to BD plus OA. Substituting BC is equal to V and OA is equal to U, we get V is equal to BD plus U. That means BD is equal to V minus U. Now, A is equal to change in velocity by time taken. A is equal to BD by AD, which is equal to BD by OC, and which is equal to BD by T. That means BD is equal to AT. From 1 and 2, V minus U is equal to AT, which means V is equal to U plus AT, which is our first equation. Equation for position-time relation. Let us consider that the object has traveled a distance s in time t under uniform acceleration a. In this figure, the distance traveled by the object is obtained by the area enclosed within OABC under the velocity time graph AB. Thus, the distance s traveled by the object is given by S equal to area OABC, which is a trapezium. It is equal to the area of rectangle OADC plus area of triangle ABD, which is equal to OA into OC plus half of AD into BD. Substituting OA is equal to U, OC is equal to AD is equal to T, and BD is equal to AT. We get S is equal to U into T plus half times T into AT. And we get our second equation, which is S is equal to ut plus half at square. Equation for position velocity relation. The distance s traveled by the object in time t moving under uniform acceleration a is given by the area enclosed within the trapezium OABC under the graph, right? So the area of trapezium would be OA plus BC into OC by 2. Substituting OA equal to U, BC equal to V and OC equal to T, we get S is equal to U plus V times T divided by 2. From the velocity time relation, T is equal to V minus U by A. Thus, using equations 1 and 2, we get S is equal to V plus U into V minus U by 2A. Thus, 2as is equal to v square minus u square. Let's see an example. A train starting from Brest attains a velocity of 72 km per hour in 5 minutes. Assuming that the acceleration is uniform, find the acceleration and the distance traveled by the train for attaining this velocity. We have been given that u is 0, v is 72 km per hour, which makes it 20 meters per second, and t is 300 seconds. Now substituting the values in a equal to v minus u by t, we get 20 minus 0 by 300, that is 1 by 15 meters per second square. We know that 2as is equal to v square minus u square. Now, since u is 0, it gives 2as is equal to v square. So, s is v square by 2a. So, it is 20 squared divided by 2 times 1 by 15 square, which gives it to be 3000 meters or 3 kilometers. Let's see one more example. A car accelerates uniformly from 18 km per hour to 36 km per hour in 5 seconds. Calculate the acceleration and the distance covered by the car in that time. Now u is 18 km per hour, that is 5 meters per second. V is 36 km per hour, that is 10 meters per second, and time is 5 seconds. We get acceleration as 10 minus 5 by 5, which is 1 meters per second square. We know that S is ut plus half at square. Substituting the values. 5 into 5 plus half into 1 into 5 square. We get S as 37.5 meters. Hence, the acceleration of the car is 1 meters per second square and the distance covered is 37.5 meters. One more question. The brakes applied to a car produce an acceleration of 6 meters per second square in the opposite direction to the motion. If the car takes 2 seconds to stop after the application of brakes, calculate the distance it travels during that time. Now A is minus 6 meters per second square. Note that the acceleration in the opposite direction to the motion. So it will be minus 6 meters per second square. Now time is 2 seconds and V is 0 since it stops. And we know that V is U plus AT. So 0 is U plus minus 6 meters per second square into 2. So we get U as 12 meters per second. So our initial speed was 12 meters per second. Now we know that s is ut plus half at square. Substituting the values, we get s as 12 meters. Thus, the car will move 12 meters before it stops after the application of brakes. Now, do you know why drivers are cautioned to maintain some distance between vehicles while traveling on the road? Let's see more examples before we move on to the next topic. A bus starts moving from rest with a uniform acceleration of 0.1 meters per second square for 2 minutes. Let's find the speed acquired and the distance traveled. The bus starts from rest, therefore the initial velocity is 0 meters per second. Acceleration is 0.1 meters per second squared, time is 120 seconds. Acceleration is given by v minus u by t. Therefore, the terminal velocity is u plus at, which gives it to be 12 meters per second. As per the third motion equation, since a is zero point 0.1, v is 12, u is 0 and t is 120, s would be v square minus u square by 2a, which gives us s as 720 meters. The speed acquired is 12 meters per second and the total distance traveled is 720 meters. Liking it? Should we go for one more example? Okay, let's go ahead. A train is traveling at a speed of 90 kilometers per hour. Brakes are applied so as to produce a uniform acceleration of minus 0.5 meters per second square. Find out how far the train will go before it is brought to rest. Initial velocity is 90 kilometers per hour, which gives it to be 25 meters per second. Terminal velocity is 0. Acceleration is minus 0.5 meters per second square. As per the third equation of motion, v square minus u square is 2as. Therefore, the distance traveled by train is v square minus u square divided by 2a. On substituting the values, we get s is as 625 meters. Hence, the train must travel 625 meters at an acceleration of minus 0.5 meters per second square before it reaches the rest position. One more. A trolley, while going down an inclined plane, has an acceleration of 2 centimeters per second square. What will be its velocity 3 seconds after the start? Initial velocity is 0, acceleration 0.02, time 3. So v is equal to u plus at. This gives us v as 0.06 meters per second. Therefore, the velocity of the trolley after 3 seconds will be 6 centimeters per second. It looks like you're getting a hang of it. So one more. A racing car has a uniform acceleration of 4 meters per second square. What distance will it cover in 10 seconds after start? The car is initially at rest. Initial velocity hence would be 0. Acceleration is 4. Time period is 10. What distance will it cover in 10 seconds after start? This is what we need to find out. Now we know, as per the second motion equation, s is equal to ut plus half at square. Therefore, the total distance covered by the car is 0 times 10 plus half into 4 minus 2 into 10 square. This gives us 200 meters. Therefore, the car will cover a distance of 200 meters after 10 seconds. Okay, one more. A stone is thrown in a vertically upward direction with a velocity of 5 meters per second. If the acceleration of the stone during its motion is 10 meters per second square in the downward direction, what will be the height attained by the stone and how much time will it take to reach there? Initial velocity is 5 meters per second. Terminal velocity is 0, since the stone will reach a position of rest at the point of maximum height. Acceleration is 10 meters per second square in the direction opposite to the trajectory of the stone. So it will be minus 10 meters per second square. Now v square minus u square is 2as as per the third motion equation. Substituting the values, we get distance to be 1.25 meters. Now, as per the first motion equation, v is u plus at. Therefore, time taken by the stone to reach a position of rest, that is its maximum height, will be v minus u by a. So, it will be 0.5 seconds. Moving on, when the velocity of an object changes, we say that the object is accelerating. The change in the velocity could be due to the change in its magnitude or the direction or both. Can you think of an example where an object does not change its magnitude of velocity but only its direction of motion? Let us assume that an athlete runs at a uniform speed on the straight path of a rectangular track. In order to keep himself on track, he quickly changes speeds at the corners. How many times will the athlete have to change his direction of motion while he completes one round? It is clear that to move in a rectangular track once, he has to change his direction of motion 4 times. As the number of sides of the track increases, the athlete has to take turns more and more often. If the athlete moves with a velocity of constant magnitude along the circular path, the only change in his velocity is due to the change in the direction of motion. The motion of the athlete moving along a circular path is therefore an example of an accelerated motion. We know that the circumference of a circle of radius r is given by 2 pi r. If the athlete takes t seconds to go once around the circular path of radius r, the speed v is given by v is equal to 2 pi r by t. When an object moves in a circular path with uniform speed, it is said to be in uniform circular motion. Let's perform an activity. Take a piece of thread and tie a small piece of stone at one of its ends. Move the stone to describe a circular path with constant speed by holding the thread at the other end. Now, let the stone go by releasing the thread. On being released, the stone moves along a straight line tangential to the circular path. This is because once the stone is released, it continues to move along the direction it has been moving at that instant. This shows that the direction of motion changed at every point when the stone was moving along the circular path. Note the direction in which the stone moves after it is released. By repeating the activity for a few times and releasing the stone at different positions of the circular path, check whether the direction in which the stone moves remains the same or not. Once released in the desired motion, the stone moves in the direction in which it was moving at the time it was released. There are many more familiar examples of objects moving under uniform circular motion, such as the motion of the moon and the earth, a satellite in a circular orbit around the earth, a cyclist on a circular track at constant speed, and so on. With this, we conclude our chapter, Motion. Take care, keep learning, keep growing, make healthier choices, be kind, Don't forget to like the video and subscribe to the channel. Have a great day. All the best. Bye bye.